Hello everyone. This is the first video of the course Signals and Systems, and in this video we will be coming up with a definition for our signal. Right? This will be the starting point. We will be mainly interested in mathematical definition, but we need to first have a qualitative definition of a signal. Now I put out the qualitative definition of signal that it is a pattern of some kind which is used to convey some message. And we deal with signals in our day-to-day life. A typical example would be you are driving a car on a road and there is a traffic light. Now, if the traffic light glows red, it conveys a message that it's a kind of a signal that you need to stop your vehicle. Similarly, if it is green, again, it's a signal, it conveys a message that you may go ahead and drive your vehicle. Fine. So formally, qualitatively, a signal is just a pattern of some kind. It should be intelligible. It should have some information which is used to convey a message. But the question is that this definition will not suffice. Fine. In engineering courses, we have a strong tendency to analyze things mathematically, which means you need a mathematical description of a signal, a mathematical model of a signal, which later on you can use to perform some degree of analysis. So mathematically, we define a signal as a function. It's a mathematical function of an independent variable. Fine. So a signal, it is represented like I've shown it here as a function x of t. Fine. And t is an independent variable. And in most of the cases, in fact, in this course and in your future coming courses in electrical and electronics domain, this independent variable is the time. Fine. Now, I want to just briefly mention here. So when I say that I have defined signal as x of t, it basically involves two quantities. Now, mathematically speaking, you will have a dependent variable which is the x that depends upon t, and you will have an independent variable which will be the variable time, that's t. Fine. Now, physically speaking, this dependent variable, we often refer this to as amplitude of the signal. Fine. So x of t is the amplitude of the signal and it depends upon the time. And this one here is the time. So we can say mathematically, if we translate this mathematical representation and definition into a physical one, we have defined signal as a time variation of an amplitude and how amplitude varies with time. Now there's a question, is our signal, generally speaking, dependent only on time? The independent variable that we have chosen in our definition, is this the only variable on which our signal will depend? Now, obviously the answer is no. Whenever we talk of a signal, a practical signal, a signal that is generated from some source in the real world, it will depend upon a lot of factors. As an example, I am talking, the voice is coming out of a mouth, so I am the source from which the signal is generating, the voice signal. But it depends upon a lot of factors. It depends upon the distance from the source and the destination, the audience, how far the audience is from the source. As we go away from the source, the strength of the voice will decrease. So it will be dependent on the distance. It will also depend upon the environmental conditions. If there's a dry environment, it may not travel to larger distances. On the other hand, if it is a humid, it will have a denser environment, the voice signal will travel further. Similarly, it depends upon the amount of noise. It may happen that I'm talking, there are people who are listening, but sidewise there is some construction work going on. So that puts a lot of noise. So that will affect the quality of a signal. So in other words, there are n number of factors that will affect the amplitude of the signal. Fine. But it is again a scientific approach that whenever we approach a particular problem, we start with simple steps. So instead of considering all those variables, the environmental conditions, the noise that is generated within the source and outside the source in the environment, we try to eliminate those conditions for starters. So we consider only prime independent variable. And you will see in this course and in other engineering related course, especially that belong to electrical and electronics domain, time is a very important parameter. Right? Hence the definition that we will be considering, let me write it down here for you, that in this course we will be considering only one independent variable. Fine. That is, our signals will be considered as functions of only one variable. And although it is time, but I will try to generalize it here that it will be a time related parameter. This independent variable, it will be time related. Fine, because you'll see that initially we will be doing analysis in the time domain, so it's time pay, it will be explicitly the time parameter, but later on we will be doing analysis in the frequency domain. So in that time will be interpreted in terms of frequency, but in any case it will be related to time and it will be a single independent variable. This is the first step approximation. Later on in your higher courses, you will see the impact of other factors. Like one of the prime factors that you will be studying will be the impact of the noise on your signal. Right? But we have a kind of a scientific approach. We always start with a simplistic model, simplistic approach. We develop our theories, we analyze based on those models, then we go on adding the complexity. So whatever analysis we do in this course, we will be considering, so it will be based on the single valued definition of our signal. That is to say, we'll be considering signals as single valued functions of time. Right? More specifically, it will be the variation of amplitude with respect to the time. Now, as far as independent variable is concerned, we have defined it, it will be time. But as far as dependent variable is concerned, the amplitude, your amplitude, it may have a real value or it may have a complex value. And accordingly, we will be encountering two kinds of signals. Either it will be a real valued signal, so the signal real valued in the sense that the amplitude of the signal, it will have a real value 1, 2, -1, -2. But we will also be discussing some complex valued signals wherein the amplitude of the signal, it is complex, it is in the form a plus iota b. Those things, those kind of signals, at least from an analysis point of view, they will be encountering in this course. So this is the definition we will be building on, that it is a signal, it is a single valued function. Sorry, it is a single valued function of time. Right? We have defined the independent variable as time and the dependent variable as amplitude. Fine. Then again, we are very much interested in the classification of the signals. Now that we have defined a signal as a function x of t, we go for the classification of the signal. And classification is based on multiple contexts. There are multiple point of views through which we can classify the signal. And one important context that we will be frequently using in this course, on the basis of which we will be classifying our signals, is on the basis of our independent variable. Now I already defined that our independent variable is time. So based on that, we have two types of signals. One is a continuous time signal, and the other one is the discrete time signal. Now these two are quite literal. So if I define my continuous time signal, so let me call it CT, continuous time, and let discrete time be called DT. Right? So a signal x of t is said to be a continuous time signal if it is defined for all time t. Right? So graphically it means I have a time axis right here, t. I am taking an interval on this time axis between 2 points t1 and t2. And between these 2 points, the signal is defined at all the points. As you can see, I have a kind of an arbitrary waveform, but it is defined at all the points that lie in this interval, whose boundaries lie between t1 and t2. So this is a continuous time signal. Fine. On the other hand, we have the discrete time signal. So a discrete time signal, it is defined only at discrete intervals of time. I will be not intervals, discrete instants of time. Fine. That means I will have a time axis, this one right here. It will be divided, so this is my time axis along here. It will be divided into small instants like 0, 1, 2, 3, 4, 5, and on the negative axis -1, -2, -3, -4. And you can have signal values only at these instants. So it will be something like this. I have a signal value at instant 1. Similarly, I will have a signal value at the discrete instant 2. I will have a signal value at the discrete instant 3. Similarly, a value at 4. Similarly, you may approach the negative axis, but the defining thing is that that means the amplitude will be defined only at these discrete instants of time, not in a continuum. So you may have a signal value at 1, 2, 3, but not in between 1 and 2. Fine. So we call such kind of a signal as a discrete time signal. Now this is the fundamental classification, the continuous time and the discrete time. And so much so that we have a separate kind of representation for a discrete time signal. Now a continuous time signal, it is defined as x of t, x being the dependent variable, t being the independent variable. But when it comes to a discrete time signal, we typically define it as x square brackets n. Both t here and n here, they represent time. Only difference is this t, it is a continuous time. Fine, defined at all the points. So we use as a notation, we use these curved brackets, round brackets. But for discrete time, n basically represents a discrete instant of time, 1, 2, 3, 4, yeah, on the negative axis. And to differentiate, we use the square brackets in the discrete time definition of the signal. Right? Now this is a fundamental classification. Now we can further go ahead, although we don't usually use that classification, but just to complete it. So if I have a continuous time signal, it can be of two types. First one will be that the dependent variable is also continuous. So it will be continuous amplitude and continuous time. So we may call it CACT. And the second one will be that it will have a discrete amplitude and continuous in time. What we can call discrete amplitude, continuous time. Fine. Now graphically, the first one, you see the amplitude, it is taking all the possible amplitude. So typically this is a CACT signal. But I may redefine a discrete version of this wherein I have the time axis, I have two time intervals T2, T1. My signal is defined at all the points between this T1 and T2, but I have a restriction on the amplitude. Amplitude is discretized in the sense that it can either be 1, 2, 3, yeah, in the negative axis -1, -2. So it can be a signal like this. So let me just have small projection so that I get an idea of the level. So it can be a signal something like this. Suppose we start from here, T1, so it has a value of 1. Then it continues for some time, then value drops to say -1. Then suppose it drops to -2. Then suppose here it raises to 2, 3. Then suppose it drops down to here. Fine. So if you see, it is defined at all the points between T1 and T2, between the interval T1 and T2. The only difference is the amplitude is discretized. You have a kind of a limit on the amplitude. Like here it is 1, here it is -1, it is -2. It is not having amplitude values between these intervals 1 and 2. So this is typically discrete amplitude but continuous time signal. Fine. On the similar grounds, we can have a classification for a discrete time signal. So we may have continuous amplitude but discrete time, what we call continuous amplitude, CADT. Or we may have a signal which is discrete in amplitude as well as in time. That is DADT. So if I quickly plot these signals, this will be the typical case of continuous amplitude because there is no restriction on the amplitude of these samples of signal. So this is continuous amplitude, discrete time signal. And if I put a limitation on the amplitude as well, so that is to say if I have signal values defined like this, 1, say here also it is 1, say here it is -2, here it be 3. In other words, I am putting a kind of a limit on the amplitude that you can only have discrete values. So in that case, it becomes a discrete amplitude and a discrete time signal. This is DADT signal. Fine. This typically forms your analog signal, which is continuous in amplitude as well as time. This you may for the time being call a digital signal, although there is one more step before we can call it an actual digital signal. But for starters, we may call that this is a closest representation of a digital signal. Fine. So there are two quantities, and depending upon whether the quantities are continuous or discrete, we may have these 4 different cases. But having said so, like I said, time is a very important parameter in electrical and electronics engineering. We normally stick to the broader classification that we classify signals only on the basis of time as continuous time and discrete time. But again, you may have these sub classifications. So we'll stop here. In the next video, we'll go for further classifications.